Okay, so let's get back on talking about diversity. So community diversity is the variety of different species that are present in the area. And there are two. There's what we call species richness, which is simply straight up the number of species that are present. And there's the relative abundance, which is the proportion of each, or rather the proportion that each species represents of all individuals in the community. In other words, the evenness, how even is the community. So if we look at pond A here versus pond B, they actually have equal species richness. They both have 4 species of frogs. However, the evenness is different, right? In pond B, the relative proportion of each of these 4 frogs is more or less equal. So we would say it's got a high level of species evenness. Whereas in pond A, we don't have very good evenness, right? We have a really large number of that green frog, and then we have a relatively low proportion of the other species. So we would say it doesn't score so well in the evenness category. So we say a community is more diverse if it has both high species richness and high evenness. And we're going to be using a tool in lab called the Shannon Diversity Index, which is a mathematical equation that takes into account both species evenness and richness. And I know you might be looking at this equation and thinking, oh my gosh, that looks complex. It's really not going to be that bad. And we're going to go over the calculations and exactly how to do this in lab. I'm also happy to post another additional video if you'd like me to on walking through these calculations. For now, I just want to talk about sort of the idea of diversity in general and why does it matter? Why do we care? Well, we care because more diverse communities are more stable communities. So greater diversity leads to greater stability. And when we're talking about a biological community, we define stability as the ability to either resist or recover from disturbance. So what is a disturbance? Well, anything that kind of usually comes in and knocks out a bunch of your species. So fire, flood, earthquake, it could be human-caused disturbance. How quickly does that community recover from that disturbance, and how well is it able to resist disturbances in the first place? So these two graphs here are kind of illustrating this idea. So in this first figure on the top here with the red line, what we're looking at is on the x-axis we have the number of species, so ranging from 0 to 25, and on the y-axis we have total plant cover. So what the researchers did here is they took experimental plots and they basically completely cleared them of all plant cover to sort of mimic a disturbance that wiped out everybody. And then they replanted them with varying numbers of species, so either 0 species or 1 species or 2 species, going all the way up to 25 species. And they looked and measured to see, within a given time period, how much total plant cover did we have? You know, how quickly did we get an actual plant cover on that plot? And what they saw is that the plots with greater species richness, with the more number of species planted, were more productive, had a higher percentage of total ground cover, kind of illustrating this principle that you're going to have a greater ability to bounce back from disturbance with more species. And the idea of why this happens is more diverse communities can use resources more efficiently. right? If we're all the same species, if everything is the same species, it has to use the exact same set of resources, and so there's more competition. But if you have different species, they can partition the resources more effectively and get more sort of biomass per unit area than you would be able to have if you had less species richness. The other graph on the bottom with the blue line sort of illustrates the same principle by using a different measurement. So again, on the x-axis we have the number of species, and on the y-axis what we have is the amount of nitrogen remaining in the soil. So what they're looking at here is efficiency of nitrogen use. In other words, if there is less nitrogen in the soil, it means that the community did a better job of using it, of pulling it up and using it. So it's another measurement of how well our community is functioning. And so what we see here is that the more species you have, the more efficiently you are using nitrogen. You're pulling more of it from the soil. So we have more kind of community function going on here, and that is a good thing. So both of these represent the same idea, that more species equals a more healthy, functional community. So species diversity is good. Now, that being said, not all species have an equal impact on the community. Some species are sort of ecological heavyweights and have a stronger effect on the community than you would expect based on their abundance. So species with a strong, let's try to spell that right, strong, we'll say strong community, a strong community impact. And there are three general categories of these species. There's what we call keystone species. There's what we call foundation species, and what we call ecosystem engineers. So these three organisms have a disparate effect on their community relative to their abundance. So let's talk about the keystone species first. So a keystone species has a strong effect despite small abundance. So two examples of a keystone species. One would be the sea otter. So the way that this works is that this keystone species, the otter, feeds on urchins. Sea urchins in turn eat sea kelp. So kelp is an algal species that makes up, in some cases, really well-developed kelp forests in the ecosystem, in the marine ecosystem. And these kelp forests are really important habitat and food sources for a huge number of organisms. And if urchins become too abundant, they'll basically just ravage these kelp forests until there's virtually nothing left. And this wipes out a huge amount of habitat for lots of other organisms and has resounding community-wide effects and basically just tanks the number of species the community can support. So these sea otters are the keystone here. By keeping the number of urchins in check, because this is what they like to eat, we end up with really well-developed kelp forests that can support a number of other species. Another example of a keystone species would be the sea star Pisaster. So Pisaster is the genus name, and Pisaster is the top predator in this scenario. So Pisaster likes to eat these mussels you see on this beach. And these mussels, if left unchecked, will completely crowd the beach and will, again, just tank the number of species that are able to live there, because these mussels are excellent competitors for space, and they'll basically crowd out any other species that tries to live there. But if Pisaster is present, it really likes to eat these mussels, and it will keep their numbers in check, allowing a much greater number of species to live there, and thus increasing the species richness due to the presence of this keystone species. So what about a foundation species? So a foundation species is different than a keystone species. They do have a large effect, but their large effect is due to their large size or their high abundance. And I think I might have misspoke in an earlier slide. Let me correct myself. So species that have a strong effect on their community, some of them have this strong effect despite small size, but some of them have this strong effect because of their high abundance. So the keystone species has a strong community-wide effect despite its small size and abundance. A foundation species, part of why it has a big impact on the community is because of its large size or great abundance. So I might have misspoken in an earlier slide, and I sorry about that. So foundation species, think about them as laying the foundation. They are big, or they're really abundant. So they provide a lot of habitat or provide a lot of food. So a good example is the fig tree that you're looking at here. It's a very, very large tree, and in some places it becomes quite abundant. So it provides habitats for thousands of insects, reptiles, birds, rodents, and is a really, really important food source. It puts out lots and lots of high energy, high calorie fruits. And the tree's physical and nutritional resources support either directly or indirectly most of the community that lives among it throughout the year. So that is an example of a foundation species. And then finally we have an ecosystem engineer. So an ecosystem engineer is a species that creates, modifies, or maintains, or all of the three, the physical habitat. For themselves and for other species. And so these guys might also be keystone or foundation species, but the big idea behind an ecosystem engineer is they somehow change the physical habitat. They might be really abundant, they might not be very abundant. But the key to being a ecosystem engineer is, again, you're somehow changing the physical habitat. And the classic example are beavers. So beavers cut down trees and build dams. I think we all know this. And when they do that, they create a pond and a wetland that wasn't there before. And this wetland provides habitat for species that would otherwise not be able to live in that area. And so we have a enormous increase. We're looking at a little spot of Minnesota here. And due to the presence of beavers, we create a huge amount of wetland that didn't exist before, creating a huge amount of habitat, allowing a highly increased number of species to live there that otherwise would not be able to live there. All right, so that is the end of chapter 56. If you have any questions, please get in touch with me. And again, we will be going over that Shannon Diversity Index in lab, so stay tuned for that. And also, if you want, let me know and I'll be happy to make a video of that. Okay. That's all I got for now, so I will talk to you